Today on the Perception in Action podcast, what is a smart perceptual mechanism? Are we missing opportunities to train the development of these smart perceptual mechanisms in sports, forcing an athlete to see in terms of simple variables and categories, where you could be training them to pick up complex information and seeing directly through the matrix? So it's time for a call to action. Hello, and thanks for joining me. This is Rob Gray from Arizona State University. I've been on a now over 25-year journey as a researcher, professor, and high-performance consultant to understand how we acquire and adapt our perceptual motor skills. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. If you're a coach or an instructor, my goal is to help you bridge the gap between research and application, and to connect your experiential knowledge with skill acquisition and motor learning theory. I want to help take you from using practice design recipes to becoming a master chef who can manipulate the key ingredients to come up with your own innovative training methods. If you're a student or fellow academic working in the skill acquisition field, I hope to keep you up to date on the latest studies and help you get to know the people working in this area. Finally, if you're developing training technologies, I hope to help you incorporate good motor learning principles in your design, pull out key performance metrics from the data, and design effective studies to evaluate your product. To learn more, help support the podcast, and/or work directly with me, please check out perceptionaction.com. Now on to the show. In today's episode, I want to look at the concept of smart perceptual mechanisms first proposed in a highly influential article by Runson in 1977. To illustrate this idea, let's imagine you just moved into a house with an unfinished backyard. You need to order some grass, so you need to know how big your yard is. That is, you need to know its area. If you didn't have the blueprints from the builder, how would you do this? It's simple. You would do what you were taught in math or physics class. Measure the length and width of your yard with a ruler or tape measure, then multiply the two together. You would get the lower order simple quantities of distance first, and then use them to compute the higher order variable of area afterwards. For most, this is exactly how our perceptual systems work too. They are designed to detect simple features, the variables from physics like distance, speed, and size, that are then combined in some way and used to compute the higher order variables we're really interested in. Another example is the perception of time to contact. If I want to know if I have enough time to cross the street before an oncoming car arrives, the traditional view has been that my perceptual system detects how far away the car is and how fast it's going, divides one by the other, and I get the calculated time. The goal of perception is to faithfully detect the simple physical properties of the world that our brain can process and use them to calculate more complex features we need for controlling our actions. But what if there was a different way? What if we could just get the variable we needed in the first place without all this need for processing and computation? To illustrate the alternative, Runson describes a device that was invented by Jacob Amsler in 1854, the polar planimeter. This device consists of two arms hinged to a calibrated roller. To use it, you fix the pole arm onto a surface and then move the other arm, called the tracer, around the outer edges of the object. This causes the roller to change its angle. If you then look at the total angle of rotation and the device is calibrated correctly, guess what you get? The area of the surface you just traced out. So if I had a device like this that was large enough, we could get the area of our yard in my original example, just by moving the tracer arm around the edge of it. If you want to see a planimeter in action, I've included a link to a video in the show notes. So why should we care about this device from the 1850s? Well, the key point noted by Runson was that with this device we get area without ever calculating the length or width of the surface first. That is, the device directly gives us the higher order property of area without need for measuring the lower order properties first. This is what Runson calls a smart mechanism. Rote mechanisms measure simple basic features that are combined in order to compute higher order ones. Alternatively, smart mechanisms, quote, are specialized on a particular type of task in a particular type of situation and capitalize on the peculiarities of the situation and the task, i.e. shortcuts. They consist of a few but specialized components. For solving problems which are repeated very often, smart instruments, if they exist, are more efficient and economical, end quote. Stated another way, smart mechanisms directly give us the complex higher order property we need for the specific task we're doing. To quote Runson, Now, if the theory of physics cannot be claimed to have a monopoly on descriptions of what is really there is no longer any reason to assume that the perceptual systems must necessarily begin by registering what is basic to physics. On the contrary, we should expect perceptual mechanisms which directly register variables of high informational value to the perceiver." End quote. This goes against another commonly held assumption in traditional views of perception. That is, what our perceptual systems are designed to do is give us a general, non-contextualized information that we can use to create multi-purpose representations. Think again about measuring the length of your yard. Length is a multi-purpose variable. Depending on what we combine it with, we could use it to calculate the time it would take an object that is moving across the yard to reach us, the area of our yard, the 3D volume of the yard up to the top of the fence, etc., and so on. Following on the ideas of Gibson, Runson argued that such multi-purpose instruments are unnecessary, overly complex, less efficient, and less economical. Why bother setting up a system that can calculate every possible variable when you only need one specific one to control your actions? This idea of getting the specific information you need in a specific situation to accomplish a goal is part of some other key ideas in motor control, like soft assemblies and task-specific devices, which I'll be discussing more in my next episode. In his paper, Runson proposes that the human perceptual system works like a planimeter instead of a ruler. That is, it consists of a smart mechanism that directly picks up the specific, complex variables we need to control our actions, rather than rote mechanisms that are used to create multipurpose representations built from simple variables from physics. There are two main reasons why he believes it works this way. First, quote, "The basic tasks of perception and the information available for them are stable properties of the organisms and the environment, respectively." End quote. By stable properties, he is essentially tapping into Gibson's ideas of information and specification. If, as Gibson proposed, there is information in the environment that is specific to the layout of surfaces, objects, and events, and the opportunities for actions these things afford, why would we not have evolved a perceptual system to pick these up directly? The idiosyncrasies, peculiarity, and highly specific context in which we perform actions are not problems that a general-purpose system must solve. They are advantages because they create specificity. The other point Runson makes here is one that Bernstein also emphasized. That is, that during evolution, one of the constraints on our perceptual system was not that it'd be easy for us to understand how it works later on. It was designed by pressures to achieve our goals and survive, not pressures to be easy to write up in a neuroscience paper. Quote, "Biological evolution might have arrived quite easily at solutions which require the utmost of capacity and sophistication of a human mind for their basic principles of operation to be understood. In other words, we should not necessarily prefer one theory of perception over another because it uses less complication in geometrical, logical, etc. principles." End quote. And since the process of discovering smart possibilities is by no means straightforward, but rather a matter of the researcher's creativity, there is no way of excluding the possibility of perceptual mechanisms which are smarter than the ones we can presently think of. This is all the more so because we must expect perceptual mechanisms to make use of invariants, which are much less universal than those of scientific geometry and mechanics, namely those of normal biological environment, or even the particular ecological niche in which the animal has evolved. Understanding how we get area by measuring length with a ruler, then the width with a ruler, and multiplying the two seems much more intuitive to us than whatever the planimeter is doing to directly pick up the answer. Because the former can be easily understood with our human-constructed principles of geometry. But being easy to understand does not mean that's the way it actually works. Another point that Runson makes nicely in the paper is that if we take a system designed with smart mechanisms and ask it to be a rote mechanism, we're likely to get a very misleading picture of how perception works. And this is really what we do in a lot of research. Imagine that we're interested in studying a skill that involves perceiving time to contact. For example, catching a ball. We need to know how long we have until the ball arrives so we can achieve the action of the goal of closing our hand at the right time to catch it. In the traditional view of perception, it is assumed that the variable time is computed from its lower level components, distance and velocity. So it would make total sense that if we wanted to understand the skill, we would first see how our perceptual system was quote-unquote measuring these lower order variables. But what if, in reality, the catcher was using a smart perceptual mechanism? That is, they were directly picking up time to contact and coupling their hand movement to the higher order information variable tau, specified by the rate of expansion of the object. Just like was the case with the planimeter, our catcher has just skipped right to the end and got to the specific information they need to achieve their goal without first wasting time detecting and processing information they don't need. If you brought someone using the planimeter or our catcher into a research lab and asked them to judge length or distance, they would be befuddled because they don't use that information. The person using the planimeter would have to maybe trace out the area around the line, maybe draw a circle around it, and then use some complicated calculations to go backwards from area to length. To quote Runson, "The fact that subjects do judge a certain variable does not prove that they possess perceptual mechanisms of an appropriate kind. When the task does not fit the perceptual mechanisms, we must expect the subject to try and compensate by using intellectual abilities, and such results will not be relevant to the study of perception." I think the same happens in a lot of sports science research. When we bring a tennis player into the lab and ask them to make a simple judgment like, is a serve going left or is a serve going right, we are asking them to be a rote instrument picking up simple variables. If they're actually a smart mechanism attuned to higher order properties of the ball's trajectory, then it's likely they will need to bring in other things to answer your question that they don't necessarily actually use on the court. Things like weighting cues, doing Bayesian type calculations, etc. In the last part of his article, Runson considers how one might develop smart perceptual mechanisms and learn to use devices like the planimeter. He notes that you can't really be told how these devices work, but rather have to learn to use them through experience and calibration. This will often involve being guided in your exploration through a coach or parent. He also emphasizes that a lot of it involves learning to better use our smart devices, or put another way, develop better information movement control laws. Quote, "Prolonged experience will often lead to increased precision and flexibility in using the planimeter. The improvement could consist both of a general increase in proficiency and the adoption of certain tricks. For example, making double measurements, one forwards and one backwards, will eliminate certain instrument errors. None of these tricks entail any changes in the instrument, nor do they require any knowledge of the theory of the planimeter. The increased precision and differentiation of perception with practice need not entail any changes in the basic principles of operation of the perceptual mechanisms, but could be due to changes in the way they're put into use." End quote. For me, the idea of smart mechanisms has a lot of other important implications for training. In particular, I think a lot of the training we are currently doing is inhibiting the ability of athletes to become smart perceptual devices. For example, when a baseball pitcher throws the ball, there's highly specific information about trajectory from its flight, related to the rate of expansion, rate of change in lateral position, spin rate, etc. This also includes information from the pitcher's delivery. So within the event of pitching, if we believe in Gibson's view, there is higher order complex information which is specific to the opportunities for action, whether a pitch is hittable or not, whether it can be driven to the opposite field, etc. Yet what do we do in training? We force hitters to see the event in terms of simple variables and categories. The pitch is high or low, it's a strike or a ball, it's a curveball or a fastball. We are forcing them to be a ruler and try to compute what they actually need, the trajectory, when they could be a planimeter and pick up this information directly. Instead of seeing what the pitcher wants the hitter to see, being fooled that a pitch was a fastball when it was really a curveball, we could potentially see through the matrix and be a smart perceptual device. How could we better support the development of smart perceptual mechanisms in practice? In a couple different ways. First, by increasing the variability of the practice conditions. Imagine that we asked someone to measure area using a ruler in a yard that was always square. They would quickly learn that they only need to measure one side and square it to get the area. By restricting practice conditions, we are creating specifying information for the particular constraints we are using, which may not extend to the constraints in competition. Developing smart perceptual mechanisms requires the specialized tasks and peculiarities of the situation Runson talked about. Second, we need to move away from tasks which ask athletes to make simple categorical judgments and or involve generalized perceptual cognitive training using non-sport specific stimuli. Being smart is all about picking up information for the specific goal in the specific situation, not developing a general multi-purpose processing system. We need to develop good hitters, not hitters that are good fastball and off-speed pitch hitters. Good golfers that can make good golf shots, not ones that can play both on a downhill and an uphill lie. Allowing athletes to become a planimeter and get information that they need directly, no matter what the specific task is. Don't force them to be rulers. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled.